In this chapter, we will talk about nonlinear kinetic, اللي هو will be our last part that is related to the exceptions that we have of the linear kinetic. Usually, the common case that we have linear kinetic, which is first order kinetic, okay, in which we have different parameters that we consider them as constants, such as K, Vd, total clearance, half-life, right? And we consider all them constants because we have linear kinetic. That's why we call this kinetic either linear, first order, or sometimes we call it dose independent kinetic or dose independent parameters. Why? Because they are not changing with changing the dose of the same drug. It will be, those parameters are constant despite the fact that we can give it with different doses or different route of administration, single dose or multiple doses. Okay, so sometimes we call it dose independent parameters or kinetic. Okay, when we had the profile of rate, whatever the rate that of the process that we are talking about versus the amount of the drug, dose of the drug, or concentration of the drug, the relationship was linear. That's why we called it linear kinetic. The same thing if we are talking about steady state concentration, if we are talking about multiple doses, whatsoever the model that we are talking about versus concentration or dose of the concentration versus dose of the drug, this also was proportional and linear. Or area under the curve versus dose of the drug, again it's linear. And those related to the relationship that we have under linear kinetic. If you remember, this depends on the model that we are talking about when it's steady state concentration and what is the equation for that. For this, if we are talking about IV bolus, let's say it was equal to this over total clearance, so it's proportional. If it's not, we have the bioavailability, and against this it's still proportional and it's linear. Okay, so directly related. This is what we know already about linear kinetic. Okay, what we know about nonlinear kinetic, it's that one, from the name, it's nonlinear, which means that it's not following linear or first order kinetic, which means that the constant that we already have or the parameters that we consider them as constant in the linear kinetic is not valid anymore. Okay, so they are changing with different doses administered of the drug via different route or single versus multiple. And that's why, one second. Excusez-moi. Okay, so that's why the parameters that we know before and what is constant before is not valid anymore for the different doses or different route of administration or single versus multiple doses. Okay, so that's why we call it nonlinear kinetic, and then sometimes we call it dose dependent kinetic because they are changing with changing the dose and the parameters that we already know, in addition to whatever you know already about the names. We call it saturation or saturable kinetic. We have a capacity limited kinetic or mixed order kinetic. Okay. Those nonlinear kinetic, we had examples of nonlinear kinetic either in absorption. When we said that we have nonlinear absorption processes, we have it in distribution, we have it in metabolism, and we have it in elimination, either in metabolism and excretion, either when we are talking about enzymes induction or inhibition, or when the metabolism happening through certain enzymes. So there's will be a saturation, and also in excretion when we talked about a renal or even bile salt excretion if it's involved a transporter. So the nonlinear pathways, we had examples on them. We have examples on them, such as when we talked about active processes. Example, a tubular secretion, if you remember, some part of the tubular reabsorption, it was related to the excretion, and also metabolism when we have CYP enzymes. Not all CYP enzymes, let's say a transporter involved. It depends on if we are within the therapeutic windows or not. If you have enzymes anyway, induction or inhibition, it's nonlinear. But sometimes the drug, we will talk about it, but the drug will have linear kinetic under low concentration or low doses, and it's nonlinear under high concentration or doses. And if the drug, as we say all the time, if the drug is linear under therapeutic window, if the therapeutic window of the drug needs low concentration, then at the end we will deal with it as linear kinetic. If not, and the therapeutic window of the drug needs higher concentration, then we will deal with it as nonlinear, and we will talk about this in a minute. Okay, so that's why sometimes even the metabolism through CYP enzymes is not nonlinear. Depends on the concentration of the drug at that time of that process. خلينا نرجع هون. Again, we call it either dose dependent, because the parameters that we know is changing with the dose, saturable or saturation, capacity limited, mixed order kinetic, and Michaelis-Menten kinetic. And we will talk about Michaelis-Menten equation in a second. Okay. As we said, it could involve any process in the kinetic processes, either one of them or a couple of them. Okay. The profile of the steady state concentration versus the dose of the drug, it should be if linear, acting like this. Okay, if it's area under the curve versus dose, again it should act like this. In non-linear, let's make it linear. Non-linear, at low doses or low concentration, it will act as linear, as I said, but at high concentration, we will have deviation from linearity. And again, it won't be that steep, but it will start as linear, then we will have deviation from linearity. Okay, and we will see why is that. You will have examples tables in which you have examples of drug goes under nonlinear kinetic, either through absorption, during absorption or distribution, excretion, renal or metabolism. Okay, so for usually what we care about in nonlinear kinetic, either we have different example of that in different processes of the kinetic. Usually we are more interested in whatever is happening in the metabolism, because it's affect the elimination overall. So that's why we usually determine whatever is happening in the elimination part. That's why you will find a lot of the package inserts, you have metabolism, and then they talk about sub-enzymes because it's one of the major nonlinear processes and kinetic. But if your drug having a dominant or a majorly nonlinear process, you need to take it into consideration whatsoever. Okay, so if we consider the nonlinear metabolism, because we have, again, if we have nonlinear metabolism and it's the drug is majorly metabolized by this process, so by default we will have nonlinear elimination, right? So it's one of the common sources, as we said earlier, one of the common sources of metabolism of nonlinearity and the drug kinetic. Usually it's related to the drug that is having interaction with enzymes to have the metabolite. And we will have drug plus enzyme to have the intermediate complex, which is usually not stable, to have the metabolite, which is our product, plus the enzyme. So the enzyme is as input will be also as output. There is a lot of, again, the details of the reaction is there in your reference book. I don't care about the details, but there's multiple assumption for this interaction, and each part of this process is involved kinetic in it and rate constant, in which we have multiple equations in which we do the differential equation for them, and then we do the kinetic modeling of each one of them to have the final nonlinear equation, Michaelis-Menten equation. We have many assumptions for this interaction, which is the simplest way to deal with nonlinear kinetic, that each one molecule of drug react with one enzyme, and we have 1-to-1 interaction either as molecules and either also as sites. So the drug is binding only one enzyme, and it's we consider that the drug is only binding to this enzyme, not other drugs involved. And also a spherical a drug usually is considered in this situation. There's a lot of assumption. Again, I don't care about the details, but at the end, once we finish the kinetic of it, we have this equation that is called Michaelis-Menten equation, okay, which is your model equation. Okay, we have this that is called the rate of the process that we are interested in. Let's say that we are talking about the rate of metabolism, or in different cases rate of elimination. It depends on what you ever talking about. And this is the maximum, it could be also called velocity. This is the maximum rate or velocity of the drug that can reach regarding the metabolism. This is the concentration of the drug, and this is the concentration of the drug again, and this is Km, which is the concentration of the drug at which it's reached 50% of the Bmax. Okay, as units, we will have this. The units are very important in this. This will be mass, its rate versus time. If this is the maximum that we can reach of the rate, so this will be mass over time 2. This is concentration, this is concentration, and this is concentration. So all of them will be in the same unit, which is a concentration unit, which is mass over volume. Okay, so this is the parameters that you have in your nonlinear equation, in which we have mechanism profile of your model in which the rate or velocity RV versus concentration of either the substrate, which is usually like this, or the dose of or concentration, sorry, of the drug. There is different way of dealing with it or writing it as symbols, either substrate or drug or just concentration. Okay, we will have this, in which again we have this. This is, we said it's a rate, so this is Vmax. You will have it on y-axis, and then we have the concentration that is needed to reach 50% of the of Vmax. This is 50% of Vmax. This is called Km. Okay, so this is the Macalister-Menten equation that we have. Okay, we have two major cases in this profile, in which we have the first case in which the concentration of the drug is very low compared to Km, which means that we are in here. Okay, the concentration of the drug is lower than that of Km. In this case, if we write the equation equals Vmax okay, if this is very low compared to this, so I can take this out. Okay, so accordingly I will have this over this multiplied to the concentration. That is equal the rate. Again, we have rate. This will be, those two parameters are constant for the same drug, so will be equal constant multiplied to the concentration of the drug. If you remember, when we have rate equals constant multiplied to the concentration of the drug, then this will represent what, kinetic wise, what order? First order kinetic. So at this area of the profile, usually the drug is behaving as first order kinetic, in which the rate versus concentration of the drug is showing a linear equation. Okay,